Hello, everyone, and welcome to another webinar from CAE. Today's webinar is going to be about controller and a little bit about vision at the end. Let's get started. So my name is Alex, and if you have any questions during the webinar, definitely email me at aes368@cornell.edu. At the end of the presentation, I'm going to take some time and look at my email and see if there are any questions and answer them. So let's talk a little about why we have a controller and what exactly do we mean by the word controller. So the answer is abstraction. It's so important I put it on there twice. Thrusters usually driven with electricity, usually supply some kind of pulse width modulation signal to your thrusters to affect their rotational speed and thus impart force on the vehicle. And this is nice, but sometimes when you want to build up an autonomous mission, you want to do higher level things such as, complete this task and ram this buoy. And that's hard to do just by working at such a low level. So the controller is meant to provide a layer of abstraction that allows you to set your motor values indirectly through higher level commands such as go forward or go west 3 meters, and then change your heading to be 60 degrees, and so on and so forth. So during this webinar, we're going to assume that to drive the thrusters, there is a method to drive the thrusters. Usually it's PWM. On CRV, we have simple brush motors, and we have an electrical team that provides a custom printed circuit board that actually sends 24 volts on and off, modulated in pulse width fashion, very fast. And we have a range of -225, which is full speed reverse, to 225, which is full speed forward. And that voltage imparts it just has some relationship to the angular velocity of the thruster's prop. So the faster it spins, obviously, the more force it's going to provide. And if it goes backwards, it provides it provides a negative force. So yeah, like I said, abstraction is definitely the key thing here. Autonomous missions should not be concerned with how the thrusters operate or how much voltage I should be supplying to each individual thruster. Missions should work at a higher level where they desire some sort of vehicle state. That usually means position and or velocity. So your mission might say, "Oh, take me to this location, coordinates 5 north, 3 east," or take me, I want to be going forward at 0.4 meters per second. Or I want to pitch 30 degrees and then turn and heading at an angular velocity of 10 degrees per second, something like that. And the way your controller operates should suit the hardware you have on the vehicle. So what we do in CAD is we can set a heading, a pitch, and a roll, or an orientation. We can desire a forward velocity, a sway velocity, and a depth from our controller. And the reason it's a little bit asymmetric in this case is, as you can see, we have x-axis, y-axis, their velocities, and then d, depth, the z-axis, is actually an absolute measurement. That matches nicely to how we measure these particular values with our sensors. So we have a compass, which measures absolute orientation, and then we have a DVO, which measures velocity, and we have a pressure sensor, which gives us a very accurate reading of depth. So it makes sense to control depth in such a direct way. Whereas position, for example, we don't have a GPS or any absolute position measurements. It's a little bit, there's an indirection there between position and velocity. So that's why we directly desire velocities and not positions. The way we've done positions is there's another layer on top of the controller that simply the mission can say, okay, I want to go to this position, and then this layer will then set desired velocities that which controller will take, and then those velocities will hopefully get you to that position. And that's usually done in a manner similar to the controller, which we're going to talk about in this presentation, but obviously a little less complicated. So let's talk about a single variable control. Let's say you have heading or something like depth, and you want to affect that value procedurally. One thing you can do is use simple proportional control, which we're going to talk about. What you need is you need to be able to measure the value and have some sort of output that affects the value indirectly, and you can vary this output continuously. So let's take an example for depth. The thrusters can be interpreted as, of course, they impart a force on the vehicle. So you can measure your depth, and you have a desired depth. Let's say you want to be at 1 meters because you think there's a buoy somewhere at 1 meters below the water. And you know your depth. Let's say you're at 0.5 meters. You just check, oh, am I above or below the desired depth? And I'm going to apply a force in the direction opposite, which will accelerate me in that direction. It's very simple binary on or off. It's a very primitive method. Something better you can do is actually scale the error from your desired. Scale your output by that error. So if you're really far from your desired, you're going to want to output a lot of force because you have a lot of mileage to get there. So this is called proportional control, and it's done a lot for simple things. So what we do is we have a constant P, or that's the gain on the controller. So that's that's usually a scale factor. If you're working with something with heading, the units there are degrees, and P is usually bigger. Smaller. Whereas if you're working something with velocity, it's usually in meters per second. So that's usually between 0 and 0.5. So if you use the same P for heading velocity, you're going to output way too much force in the heading case because the units just are that much bigger in absolute scale. So P is kind of there to scale it and down, so you have like a unitless kind of force output. And you multiply that by your desired depth minus your current depth, or desired value minus your current measured value. And if you're at your value, that difference is 0, so then you don't go anywhere, which is what we want. So this works well. It's a simple starting point, and it's kind of an obvious thing you could try, like the stepping stone for controllers. But the problems with this is that sometimes there's overshoot. So if you notice, as long as you're above your set point, your set value, your desired value, you're going to produce a force taking you down. And then in most systems, when you're at that desired point, you're going to have some momentum, if you want to call it that, going in the other direction. So that leads to overshoot. And usually the system ends up oscillating around that desired point, maybe decaying, but still you don't want those. You don't want it to get there and stay there, not just to go back and forth around this desired set point. So one natural extension of this proportional control is to add a derivative term, which essentially measures how fast you're approaching your desired point. So it's kind of like adding a negative force to slow you down. So let's say you're approaching your desired very fast. The derivative is high, and then you're going to say, okay, I'm going towards my desired very fast. Let me scale that down so I don't overshoot. And it takes some tuning a little bit with the proportional gain and derivative gain. That's the capital P and capital D that scale each term in this equation here. And it takes a little bit of tuning. But once you get that, you should have a pretty nice response, step response. So it should be aggressive. So you should have high enough P. And it should also not overshoot once it reaches the set point. So a high enough D as well. If you make D too high, you might that term might dominate the equation, because especially if your signal is very noisy, because obviously derivative isn't something you get for free. Usually the simplest thing you can do is take the difference between 2 points and divide the time between them. And if you have a noisy signal, that can be artificially high. And if you have a high D, leads to a noisy signal, that leads to more oscillations, leads to more high D, and you'll know it'll become unstable if you make that too high. So a PD loop is actually a lot more effective than a P loop, and a lot of our PID loops we use on CAV are PD loops. Another extension you can do to this scheme is add an integral term. So that's where the term PID comes from, proportional integral derivative. So one problem with proportional derivative loops is that if the system is such a system, there might be some steady state error. So if there's some force preventing it, or some steady state disturbance that is preventing you from reaching your desired set point, the PD loop may not be sufficient to get you there. That's a problem that's also there with the P control, because if you need to overcome a force to reach a particular set point, and the proportional gain is too low, there's nothing in there that will increase that force, the output of the controller, based on how long you've been stuck by pushed back by that force. So the integral tries to capture that by integrating the error, and that's essentially adding a force is proportional to the time spent in error. So the longer you're away from your set point, the output's going to increase until that starts to decrease, hopefully. If you're using this for depth, this effectively learns the buoyancy force. So if the vehicle is positively buoyant, it's always going to be pushed naturally towards the surface. If you're trying to maintain depth with a simple P control or PD control, it's never actually going to hit the desired point, because let's say you're at your desired set point, your P term is going to be 0 because the error is 0. But of course, so you're outputting no force in that plane, but the buoyancy force is pushing you up, so you're going to start drifting up a little bit. That's not ideal. What the integral term does is it says, okay, I've been too close to the surface. The integral term is going to pick back up, and this is some kind of state that's usually stored in the PID loop. It needs to be persistent from iteration to iteration, obviously, because it's essentially memory. You're learning what happened in previous time steps, exactly how much you've been in error. And then that's going to increase until the value of that integral term is in some way related to the difference between the buoyancy force and the gravity force on your vehicle. It's essentially poor man's system characterization, because it allows you to learn and kind of sweep under the rug certain complex terms that you don't want to worry about modeling, and it can be nice in that sense, but it's also going to be a little bit clunky because it's ideal. It assumes kind of it's a steady state, it's always there. There are schemes you could do which clear the integral term when crossing 0 or some predetermined value. For example, drag. The integral term can be great for learning drag, but as soon as you go back to 0 velocity, there is no drag anymore because you're not moving. So ideally you want that integral term to be zeroed out when you're not moving, and scale proportionally as you're increasing velocity. We're going to talk more about drag estimation a little bit later. So let's talk a little about system setup. These PID loops, they work great in one dimension. It's pretty clear how to use them there, but it might not be clear how to extend them to into one AUV controller. Just an aside, you can also use them. They're not limited to one dimension. You have to use them for other things. You make a quaternion PID loop, which it doesn't output a single real valued. It actually outputs a axis output and a scalar that scales that axis. So that's something we do for orientation on CUAV. We have a quaternion PID loop, which handles our orientation. We have a desired x velocity, a y velocity, and a depth PID loop. Alternative you can do is an alternative to the quaternion is have one for each degree of freedom. So that would be one for x velocity, one for y velocity, one for depth, but also one for heading, one for pitch, and one for roll. That might be simpler if your system doesn't support quaternions, or there's really no need to go to that level of complexity. Quaternions are very nice because they allow you to kind of they don't make any assumptions about how level your vehicle is. So a lot of schemes that use Euler angles like heading, pitch, and roll will assume that your pitch and roll aren't that high, because as soon as you start to pick up some pitch, your roll axis and your heading axis aren't orthogonal anymore, and that can complicate things. So in some way, the quaternion math is simpler because it doesn't really care what the orientation is. It's one simple, well, not that simple, but it's a very concise way to express your orientation. So let's talk a little bit about how you combine these PID loops. So you have all these PID loops, sure, but how do you actually get the AUV to go anywhere? So what you can do is interpret the output of these PID loops as desired acceleration. So each PID loop is running in its own degree of freedom. You have your x velocity, y velocity, and they're only concerned with their own thing. And they're requesting an acceleration that's going to help them to achieve their set point. They don't really know about the other PID loops. And in order for that to hold up, they should ideally be independent. So that kind of holds because you have x velocity, y velocity, and depth. An acceleration in one axis doesn't really affect another axis. So that's good. Pitch and roll, heading, pitch, and roll a little bit become dependent once you start pitching. So quaternion PID loops work great there. And what the quaternion PID loop will do is request an angular acceleration about some axes. And like I said, the x, y, and depth PID loops, they request linear accelerations in their respective axes. And what you could do is you can actually combine these acceleration vectors. So if your PID loops, if your x PID loop requests an acceleration of 2 meters per second in the x-axis, 2 meters per second squared in the x-axis, and your y PID loop requests an acceleration of 2 meters per second squared in the y-axis, the total acceleration requested is just the vector sum of those two quantities. So it'd be, I don't know, 2 radical 2 at 45 degrees from the zero heading, or however you want to, whatever your reference is there. So that's really neat. Vectors are additive. You can also add angular accelerations. So you can take the output of all your PRD loops and convert them to a force. You convert them into an acceleration and an angular acceleration vector, and then add them all up together. And now you have a single linear desired acceleration and a single desired angular acceleration. So the angular acceleration is for orientation, and the linear acceleration is for translational degrees of freedom, x velocity, y velocity, and depth. I'm going to talk a little bit later about why we're interpreting this as acceleration and not force, because you might think, oh, force is the most direct way because my thrusters impart a force, not an acceleration. But we're going to talk about that later. So how do you actually go from this desired acceleration into thruster values? We're going to talk about thruster mapping. So first, what's a good idea to do is convert your desired acceleration to a desired torque. Now, for linear values, this is very simple. This is just mass times acceleration. So you have a desired acceleration, multiply the mass, the scalar offset. I might think, oh, what's the big deal? It's just a value. It's a unit conversion. It doesn't really change anything and qualitatively about the quantity. That's correct. Where this really comes into play is in angular accelerations. So you want to convert your angular accelerations to torques by scaling them with the moment of inertia matrix, which is a 3x3 matrix that kind of captures the way mass is distributed around your center of mass for the vehicle. So that's really important if you're trying to do some kind of, especially if your vehicle is very, very long and not wide. So we have this Sunseed, we have a very slim and narrow vehicle, but it's also very long. So it so happens that it's really easy to roll it than it is to pitch it. So a desired acceleration in the roll axis will need less torque to achieve than the same magnitude acceleration in the pitch axis. So the moment of inertia kind of captures this and is able to do this conversion for us. The way you can calculate this moment of inertia is if you have a SolidWorks model of the vehicle, there are tools in there that will help you do that. They actually output all sorts of cool dynamical and physical quantities about your object. If you don't, you can always estimate it. A rough order of an approximation is always good, especially if you have such a usually between pitch and roll is the one I usually see. It's most different, and that can kind of help you correctly calculate the torques needed to impart angular acceleration on the vehicle. So once you do that, you have a desired force and a desired torque. And the thrusters output forces, which is great because you can go from these forces to a total force on the vehicle. What you do is you sum each contribution from each thruster and then add them all up like vectors. So to get the force, you just take a thruster. For each thruster, you can do this. Here's what you can do. Each thruster has a position and an axis in which it is pointed. So that's the direction it imparts force. And it's probably a good idea to have some sort of system where you characterize these in a simple configuration file and say, this is where my thrusters are. There are n of them, and this is where they're pointed. And once you have this dynamically in the system, you can just make this all automatic. So the force output by the thruster will be the scalar force multiplied by the axis. That's just it's going in the direction of the axis times the amount of force. The scalar force is just how much force that thruster is providing. The torque is just R cross F. So that would be the position of the thruster from the center of mass. And the center of mass is something, again, you can calculate using SolidWorks, or obviously it's usually somewhere near the center of the geometric center of the vehicle, unless you do something really crazy. So that should be pretty easy to kind of roughly estimate. And then you can measure the offset that your thruster is at. So your torque is going to be your position crossed with this value. So which not only can you add all the forces together, you can also add all the torques together. So each thruster outputs a particular torque, and then you can add those together, and that's the total torque imparted on the vehicle. What you can do is put all the thrusters axes in a matrix as a column, and then you have this vector, which will be a list of forces you want each thruster to output. And if you multiply that matrix with that vector, you can get either a 3 or a 6-dimensional vector that is the vector of the force vector that is on the vehicle, given those thruster forces. So this matrix A, which I'm just set A here just because it was the first letter of the alphabet, this characterizes where your thrusters are pointing and how their force provides a torque on the vehicle. So this can either be a n by 6 matrix, sorry, a 6 by n matrix, or a 3 by n matrix, depending on whether you want to do forces and torques together. And then the output will either be a 3-dimensional vector, which is just force or just torque, or a 6-dimensional vector, which is force concatenated with torque at the end. So that's nice. You can calculate how much, what's going to happen to the sub, what are the forces on the sub given a set of thruster forces. But you might think, oh, I should probably want to go in the reverse. Yes. So you have what happens is you have a desired torque and force in the vehicle. That comes from the PID loops. So we added all the PID loops together, and we had a desired acceleration. Then we made a desired force. We had a desired angular acceleration, and then we made that into desired torque. But we really want the x, the vector of thruster values that are going to get us there. Because we want to assign each thruster a voltage, or which really should correspond to a force that's going to result in that desired force and desired torque. So you can just, logically, we can think of it as inverting A. Sure, A is not square, so you can't really invert it. But there are definitely solutions that will solve this very efficiently. You want to get the minimum norm solution. There's actually a neat formula for this you can find online. So that's going to get you the set of thruster forces that are going to, when multiplied by the matrix, give you the desired force and torques. But there is a catch there, actually, because, of course, your thrusters aren't infinitely powerful. The solution returned here might give you a force for a thruster that thruster simply can't provide. So if your thruster, say, at full power provides only 5 newtons of force, and a certain desired torque and desired acceleration requires that particular thruster to output 7 newtons of torque, well, you're kind of screwed there. You can't really do that. So what usually happens there is that actually becomes a bounded minimization problem, where you can actually make an objective function that is the error in your outputted in your desired force and desired torque, and what's actually going to happen with the thruster values. So when that happens, what you can do is run some kind of black box minimization solver on your space to find the set of thruster values that minimizes the error you're going to have. You might say, why not just clamp the values at max force? Yeah, that would work, but it's not ideal sometimes, because you might want to have some priority over which degrees of freedom get preference, right? So if your PID loops output things that are crazy, and one wants to go a really high angular acceleration, and the other 3 want to go really fast in one linear direction, it may be a good idea to prioritize torques so that your vehicle has a stable orientation. So we can do that's simple to do with the black box routine, because then you can just set add a scaling to the objective function for that particular error term. Whereas you just clamp the values, you can't really capture that. Anyway, so that's great. Now you have a set of thruster values that has desired force. But wait, so this force is coming from the thrusters. But the PID loops, they don't care where the force comes from. So there are other ways the vehicle has forces on it and torques. The main one, the one that's huge, is buoyancy, right? So if your vehicle's center of gravity is different from your center of mass, there's going to be some buoyancy torques imparted on the vehicle when the vehicle is not at 0 pitch and 0 roll. Another one is drag. Obviously, as you're moving, the water is going to pull you in the other direction. So that's going to impart a force in the vehicle. And there are always outside forces that are impossible to anticipate, like currents in the water, someone kicking your sub, or someone pushing it. You can definitely react to those forces, but you can't really anticipate them. So what you usually want to do is take this desired force from your PID loops, and before feeding it into this thruster mapping solution, subtract all the passive forces in the vehicle. So that makes sense because your PID loops, they just want the sub to have those accelerations and angular accelerations. They don't care what forces get it there. So you don't want to duplicate forces that are already in the vehicle by the passive forces with your thrusters. The way this is applied practically is one of the biggest benefits comes from, I know at least for CAV, was roll control and pitch control. So if you're trying to maintain zero roll, right, and you're slightly rolled one way, you might say, okay, I'm too high on one side. So the PID loop is going to say, okay, I need to output a torque that's going to roll me, an angular acceleration that's going to roll me back down to 0. So the PID loop says, I want an angular acceleration. And the controller is like, okay, I'll give you an angular acceleration with my thrusters. And it does that. But there's also a passive force that tends to roll the vehicle upright, right? That's gravity and buoyancy working together, kind of like passive roll control, if you want to say that. And then both of them are acting together, and the vehicle ends up overshooting the 0 roll and kind of just like oscillates in the cradle. So a smarter thing you do is have the controller be aware of these passive forces. So then the controller will be like, okay, the PID loop, you want to force a torque that's going to, an angular acceleration that's going to roll you back. Well, look, buoyancy is already providing that acceleration. So I'm not gonna do anything. Let the vehicle bring it down. Let the gravity bring the vehicle down. That actually, if you have oscillation problems, this will fix them if this is the cause, of course. So this was a problem with us, and we added this model. We added this force, these passive forces, abstraction, and we stopped oscillating, which is great. Yeah, let's talk about a little bit more force estimation. What happens is if the center of buoyancy is not at the center of mass, and center of buoyancy is usually it actually is the geometric center of the vehicle. So the water your vehicle displaces when it's in the water, the center of that water is where buoyancy will act. Gravity always acts at the center of mass. So if there's any kind of translation offset between the two, they won't be acting through the same plane there. So you can see in this picture here, if there's any kind of pitch or roll in the vehicle, there's going to be a restorative torque that's going to roll it back. So here you can see R cross F. If you take your fingers and point them in the R direction and point your fingers, curl your fingers in the F direction, you'll notice that your thumb points into the screen and your fingers will curl in a clockwise way, bring the vehicle back to level. You can see it's tilted here. So that's how passive roll, passive pitch come to be. Other forces you can estimate are drag. So this is something that increases with velocity. So what you can do is make a model that takes in your velocity and angular rotation even, and tries to come up with some accurate force on the vehicle due to drag, and then you can use that in your force estimation. What you can do is also, if you have a SolidWorks model, run some. I know there's some software out there that can actually run these simulations, give you a very accurate model of the hydrodynamic profile of your vehicle. You can use those studies and experiments directly in your model. A simple thing you can do if you don't have that option is to kind of segment your vehicle into planes. The more planes you have, the more kind of degrees of freedom you can capture. So sometimes there are forces induced in the vehicle due to kind of the Bernoulli effect. So some parts of the sub might be smoother, and then if you're swaying, and then the back of your vehicle, it looks a little bit differently than the front of your vehicle. There might be some kind of heading torque induced there. So to capture that in your model, you're going to need to have maybe a plane in the back and a plane in the front of the vehicle that have different properties, and then that can capture that induced heading torque due to drag. So force estimation is important because it takes the work off PID loops, right? So the PID loops just want this angular acceleration. They don't have to know based on what my current value is. Oh, what should I do less or more? They just say, oh, I want this to happen to the vehicle. This acceleration, this angular acceleration, and we take care of all we split that up between thruster and passive in the controller. One more point that I'd like to bring up is thruster characterization. So we've been talking about giving each thruster a force, but we really can't just do that. We can't say, okay, give me 2 newtons. You can give each thruster a voltage, or usually it's a PWM. So how exactly is that mapped to force? Is it linear? Is it nonlinear? Well, what you usually do is you do experiments. What we do in COV is we have this rig that kind of, you can mount the thruster on it and then fire the thruster at a particular voltage, and then see exactly what the force is, what force that is producing. And that's we actually measured the torque imparted on this lever, and that's converted to a force based on, we know exactly how big this rig is. So what we usually do is you can curve fit to these data points. So you can say, okay, from this thruster at 0, 10, 20, 30, 40, so on and so forth, PWM, and then see how much force it's imparting. And then make some kind of model or a lookup table. So then when you want to calculate the force for a given PWM or the reverse, you can look up what happened in your experiment and then say, okay, here, this is what the force is going to be. Usually what we do in CUV is we have a quadratic fit. So the module, you can just look at the data and say, okay, it looks like it's a quadratic a relationship between voltage and force. So we fit a quadratic curve to it, and then we want to calculate the PWM to achieve a certain force, which is what you want to do in the controller, is you invert that quadratic regression. So it's pretty simple to do. It's actually quite important because if you think your thrusters are doing, if you think your thrusters are too strong or too weak, you might result in an unstable control or a very sluggish control. So if your thrusters are more powerful than you think they are, that might lead to oscillations and jitters that the controller really isn't anticipating. If you think they're weaker than you think they are, then that might result in unnecessarily sluggish control. So it's important to have a good thruster characterization. So obviously there are more complicated things you can do. This was just what we do on CUAV, and we're trying to do these more complicated things. Some kind of online characterization is nice because this model that we have, you need to, like we calculated, you need the moment of inertia matrix. You need to know where the center of buoyancy is, and but these things, they're already kind of, you can observe them based on the vehicle's outputs, right? So the information is there. You shouldn't do the same thing twice expecting different results. If your model is mischaracterized and you do something and you don't get the desired output, there should be some mechanism where you can say, okay, this is not right. Let's update our model based on what we saw. So there are a lot of schemes that do this. There are a lot of cool papers about this you can read online. I hope I've inspired you to do some research on your own. There are a lot of models that kind of update the model based on what happens. Usually some complicated scheme with Jacobians and whatnot and cool stuff. But yeah, definitely check those out. All right, yeah, this is the end of the control presentation. If you have any questions, I'll be here for 5 minutes. Send them to my email, aes368@cornell.edu. Thanks. So we have one question coming in from Andrew. It says, where is the controller on your vehicle? So that's a good question. The controller runs on our Linux computer, so it's entirely off board. Our thruster board just takes in desired PWMs for the thrusters and gives that voltage to the thrusters. There are a lot of teams out there that do a controller in firmware. That might work better. Obviously, it's more. I guess it's more. It's in real time. You have more updates, but we found that it's nicer to have this kind of ease of access and ease of tuning to the controller. And of course, speed isn't really an issue. We use Python for our controller. NumPy is great. It gives you the speed of C with the ease of use of Python. So our controller runs just as another Linux process on our submarine, and it's worked out quite well for us. Okay, looks like there are no more questions. If any come up, definitely email me. I'll be happy to answer, not just until the end of this webinar, but for a few years, hopefully. Yeah, definitely. I hope I've inspired you to do some research on your own, and good luck controlling your autonomous underwater vehicle. Now we're going to do a little bit of segment about vision. This has been a combined webinar. This last part is going to be short, but it's going to give us an overview of what exactly we do on CUAV for vision. Okay. Again, email me AES with questions for vision as well. So why vision? Well, you want to affect your environment, right? As a submarine, you need to be able to recognize things, to act on them, and to take certain action. So I hope I shouldn't have to motivate this too much. Vision is important. You need cameras, or some kind of perception. Sonar is cool, but it has slow update rates and it has not a very big field of view. Color cameras are great if you have light, because it's fast. You get 30 frames per second. A lot of information there. The images are huge, very nice resolution. In terms of camera choice, on CUAV we usually go with we usually go with this USB camera or FireWire. Lately we've had some Gigi cameras, which have been a little sketchy, but they've worked out. All right, yep. The tools. What do we use for vision processing? Well, of course, the digital camera requires color images. That's very important. And then that gives you a two-dimensional array of pixel intensities. There's usually 3 channels: red, green, and blue. The red value is how much red there is in that pixel, and the green and blue do the same for green and blue. The library we use is OpenCV. I think that's Open Computer Vision. It's a great library. A lot of contributors. It has a lot of awesome vision processing tools. And the great thing is it has bindings for C++ and Python and probably other languages if you want to use them. The Python ones are great because they give you ease of use with the speed of C, because your Python call actually is not implemented in Python. It calls some optimized C or Fortran routine or whatever. So that's what we use almost exclusively OpenCV for these algorithms. And we're going to learn a little bit about some of these algorithms in the webinar. This is going to be just a short kind of overview of how we've done vision for CUAV to detect mission elements such as buoys, pipes, bins. By pipes, I mean those orange path segments that tell you where to go, and other elements in the pool that are visible to the naked eye and to our cameras. So we can split that process down into a few essential steps. We got color space selection, where we can, we're not limited to the RGB color space. We can convert that into other color spaces if it's so suited for the task. And then from that color space, we choose a channel. So something like we'll choose the red channel or the green channel. You know, if you're looking for a red object, you'd think, oh, I just choose the red channel. Yeah, that might work. So that's what we're talking about, segmentation. Then after segmentation comes thresholding, which is you will take this single channel image and convert it into a binary image. And after that, you can filter that binary image to get rid of any artifacts or really hone in on your object of interest. And then after you filter, you usually want to do some sort of contour detection, which is going to detect the shape or the object you're looking for. And then after that, there's usually some ad hoc processing that's kind of specific to the task at hand. So color theory is a big field. I encourage you to check it out in your own time. There's a lot of cool stuff there. But really the thing that's important for vision is the thing we found here on CUV is that certain channels of certain color spaces, they make for easier thresholding. So you might think, okay, you know, I'm looking for a red buoy. Let me just use the red channel. I mean, yeah, that actually doesn't work as well as you'd imagine, because you know, the buoy is red, sure, but it's not entirely. It's not 25500. It's not entirely red. Other objects also have red in them. For example, like white. White is just as red, from that perspective, because white is 255, 255, 255, and if you just look at the red channel, a white's gonna be, you know, it's gonna be red. You can do some kind of look at the difference between the red channel, and the blue channel, and the green channel. Yeah, that's something you can do. But there are other more complicated color spaces like LUV, LAB, HSV, hue saturation value. That kind of looking at each channel from each color space, you can kind of get a sense for what's going to stand out in that color space. So usually the way we do that is by inspection. Just give me the images of all the color spaces, and see if I'm looking for an orange path segment. Let me see in which grayscale image the pipe's going to be most distinguished from its background. And what I mean by grayscale images, each of these color spaces have 3 channels most of the time. So 3 channels. Each channel has a single value per pixel. So it's grayscale. Usually it's 0 to 255, or you can have continuous HDR or some stuff like that. And OpenCV has a lot of function calls that make this conversion very easy. You can just call CV convert, and it's going to take you from one color space to another. A more advanced thing you can do is do some sort of dynamic. Maybe if you know a thing or two about color theory, you can design your own color space that works perfect for this task. Oftentimes we have 2 competing channels that look promising, and none of them are. Both of them aren't quite perfect, but they're the 2 best, and you only wonder, oh, what if there was something in between that worked even better? So if you have, you definitely explore that area for segmentation. So yeah, once we have our channel, we've selected it from the color space, we can run thresholding on it, and that's just a fancy term that means choose which pixels to turn on or off. So the input is a single channel image, which is a grayscale, and then the output is a binary image, which is just black pixels or white pixels. And simple thresholding is what you might imagine. You pick a value and say, okay, turn on all the pixels that are above or below this value. So if you're looking for something red, what you might say is, okay, turn on all the pixels that have a red value greater than 200 out of 255. That works okay. That's a simple thing to do. You definitely have to tune that to get it to work. But the drawback is that in different lighting conditions, the values change on an absolute level. But the idea is that the relative values of one object to its background shouldn't change too much. So that's where adaptive thresholding comes in, and that's going to be more dynamic and more robust to changes in lighting. And what that does is it doesn't just compare the pixel's intensity to intensity you supply, but it compares the pixel intensity to surrounding pixel intensities. So that kind of it's meant to turn on pixels that stand out, which is exactly what we want if we choose the color space correctly. And there's some parameters you can pass it in, like block size, which tells it how big of a neighborhood to consider, and a single value parameter that kind of I think it's a threshold for the difference between the current pixel and the surrounding pixel. And you can definitely read up more about adaptive thresholding. There's some cool algorithms. OpenCV has a function, adaptive threshold, which does exactly this. And it's great. So it's a single line in C++ and Python. And this is the behavior that we're trying to optimize for in channel choosing. So we want to choose a channel that, when thresholded, is going to give us a nice, clean, binary blob of the object we're looking for. So we have this grayscale image that has, let's say, if we're looking for an orange path, there's going to be some rectangular-looking, either really gray or really dark object that stands out from its background. And then when we threshold, well, ideally what we want is the image is all black, except for a white rectangle somewhere in the screen, which will be our path segment. So after you do the thresholding, some filtering might be necessary. Thresholding may leave some artifacts if your thresholding isn't perfect. So maybe simple specs or objects that clearly aren't the object you're looking for, but they're kind of in the way. Maybe ripples in the water occasionally get picked up. One trick you can do to get rid of that is there are these 2 functions called erode and dilate. And erode, I mean, they do what they think they do. Erode takes each kind of blob of turned on pixels and shrinks it. Then dilates, expands it. So if you do this on an image, large binary blobs of white pixels will be unaffected, because you're going to make them smaller and then make them bigger. So the end result should be the same. But small objects, they can disappear, right? So if you have a small enough object that's eroded away, when you dilate it, there's nothing to dilate, so it just doesn't come back. So that's a nice way to get rid of artifacts that aren't what you're looking for. Data can also be used on its own. If your thresholding is too picky, you can use it to fill in gaps in the binary blob. That's just something you can add in by inspection if you notice thresholding is not working. Other more advanced things you can do is do Boolean operations on your binary images. So that's just a pixel by pixel Boolean operation. What you can do is threshold two different color spaces and or XOR them, whatever makes sense, to get a third threshold, a third binary image that you can then filter and do the rest of the processing on. Well, that might be useful if you have some sort of, if they're two thresholding that aren't perfect, but they complement each other in nice ways. So for example, one takes the bottom half of an object and the other one the top half of an object. If you combine them and then OR them, then you have the entire object. That's just a simple example. And you can do more complicated things. That's kind of like a case-by-case thing, if you notice, for certain elements. It could be neat to try. After you have a binary image that kind of makes prominent the object of interest, there's this great function, find contours, which finds, it basically puts a perimeter around every binary blob and all the subblobs inside, and returns them. This is great because when you're looking for things, you want to, let's say you're looking for an orange path segment, you're looking for a rectangular object that has straight lines and a particular aspect ratio. So once you fit a contour, once you find all the contours, you can examine each contour, look at things like its size, its aspect ratio. You can do box fits, circle fits. So if you're looking for a buoy and you find an object that has a really poor circle fit, so when you do a circle fit, there's a way to find out how good the fit is. If you do a circle fit on a potential buoy contour and you see that the circle fit is horrible, it just looks nothing like a circle, it's like a line or something, it's probably not a buoy. But if you're looking for a path, you want to do a box fit and see how boxy it is. Maybe calculate its aspect ratio. To see if it's a good candidate for a pipe. And then if it is, you'll say, okay, this is probably the pipe or the buoy we're looking for. Another thing you do is use this to calculate skew. So once you have the contour, you can see the difference in the left edge and the right edge. And then there are functions that help you do this from OpenCV. Like all other cases, OpenCV is great. You can fit a kind of a quadrilateral on it, and then see if two sides, if two of the sides, at least for a rectangular object, are different in size. And if they are, you're probably skewed a little bit. So that can be useful information so that you can go in the direction that's going to unskew you from your approach. And then the last thing we're going to talk about is once you have your contour, you can calculate its x and y. You can calculate its size, and then obviously the x and y is used by your mission to center on the object. So, but you might want to do some kind of shape classification. So, for example, past year drove stuff with Space Invaders. So you have a bunch of contours, and you want to say what Space Invader is this? Because you want to identify a particular shape, yes, or a particular number. For if the speed limit's 2 years ago, you want to see which number am I looking at. What you can do is calculate these image moments. They're called hue moments, and you run it on a contour. OpenCV has an algorithm. It's hue. You call hue on this contour, and then it gives you 7 numbers, kind of like a 7 vector, that are scale, rotation, and reflection invariant. So that's great because it means if you have a scaled down version of the object and it's a little bit rotated and reflected, reflection is not really important for our case, but the scale and rotation are big because if you scale it and then rotate it, it's going to give you the same hue moments if you didn't do that. So that makes sense because you can see why that's important, because if you're high up, if you're really far from an object, it's going to be smaller. If you go closer, it's still the same object, right? If you rotate it with respect to that object, it's still the same object, just the contour is a little different. So what you can usually do is calculate the hue moments of each contour and then compare them to kind of classify. So what you can do is take reference contours for your 4 Space Invaders, and you obviously know as a human you can identify them. You can tag those, and then when in real time you're calculating hue moments of potential Space Invaders, you can see how the distance. You can do a distance minimization from the hue moment of your contour to the known reference contours, and then the known reference hue moments. And then you can say pick the shape that has the hue moments that are closest to the one you're examining. And of course, machine learning is a natural extension to this. You can feed this all into some learner. You have tagged instances, and you can make a classifier. And your feature vector can be the 7 hue moments. And then it's probably going to do some sort of, classic machine learning thing, SVMs, see how far they are, stuff like that. You can also augment your feature vector with other attributes that the contour perhaps doesn't capture, the hue moments don't capture, like number of holes. If two things have the same shape, but one has a hole and one doesn't, the presence of the hole is information that your learner can use to distinguish between, or to more accurately classify objects. Things like hole size as well can be used. So that's just a way to augment your machine learner. And obviously, this was just an overview of what we do. Most of the time, there are obviously more advanced techniques you can use that will do better and are probably smarter. So one thing you can do is edge detection. OpenCV has a whole slew of algorithms that claim to do edge detection. Those work for you, great. There's also optical flow, which is really important if you think about it, because it kind of provides temporal tracking. The approach we just described kind of processes each frame without any history, which is really stupid, because if you see a buoy one frame, there's no reason to suspect that the buoy is not going to be there the next frame, right? It's still going to be there. Your sub doesn't move that fast. So optical flow kind of uses this history to more track points of interest in the image. And what we really need is if you could give hints to this algorithm based on what your vehicle is doing. So kind of characterizing your camera and saying, okay, if I'm strafing and I'm rotating in this way, the objects in my image are going to move in this fashion. So then you can say, potentially you can have some Bayesian model that takes in your velocities and the image output and says, okay, if I'm moving at this rate and the object is in this image, is here in my image, the most likely position for it in the next frame is going to be here. And this is going to be related based on your physics of your camera, your field of view, your camera distortion parameters, and so on and so forth. That's definitely kind of the next level thing you can do. And we're definitely experimenting with that on CUAV. So a lot of these things are easy to kind of test an area with OpenCV because so many things are already implemented for you. If you see a vision algorithm from a recent research paper online, there's probably a good chance OpenCV has it implemented as some kind of experimental suite. So definitely experiment and try things out. And I hope I've inspired you to do some research on your own. All right, yeah, if you have any questions, email me. I'll be here for 5 minutes answering questions if any come up. If any don't, definitely email me later on. If you have any, I'll be happy to answer as best I can. Thanks. We have one question coming in from Blendy. It says, essentially boils down to how far can the vehicle see? Well, I would say in the order of about maybe 5 to 10 meters. Anything more than that, unless you have a really high resolution camera, it's difficult to discern objects. And a lot of the algorithms we use depend on there being some kind of minimum size to distinguish between specs and objects. So we're really dependent on our navigation to get us to where we think objects are, and then we start looking for them once we think we're sufficiently close. But it definitely may be advantageous to look for objects all the time, even if you know you're not close, because those vision updates can be used to localize the sub, right? If you see an object in a particular position on your camera, that tells you something about where the sub is in the pool, as well as where that object is. So there's kind of like a dual update you can do there. Thanks, Bundy, for your question. We have one more question here from Anonymous. It says, how does vision work in the 5th dimension? Well, I've only been there once or twice. I didn't really bring Gemini, which is our autonomous underwater vehicle there. So I didn't really get a chance to experiment. There were more important things to do. But next time I'll definitely check that out. Let you know. I'll get back to you. And I think that concludes our webinar. So thank you for watching. Be sure to tune in for future webinars. And again, if you have any questions, email me. I'll be happy to talk about anything you want to talk about. So have a good day.